Okay. Um, Homework questions.
Can we get an extension?
Um,
I know it's optional, but still.
yeah, I look at it this way.
Okay.
Whoever turns it in, by tonight, and so far one person has. It's not like I'm chomping at the bit to look at them and I can't wait to grade these things. That's not true. So, so yeah, also there will not be another assignment due in this class for quite some time. So, yeah. So by all means, yeah,
March 1st.
Something like that. Right.
Thank you, man.
Okay. All right. So, as I just calculated, how far away is March 1st? But yeah. Okay. All right. So, I should mention, and I don't know what is up with Canvas. There is a new Canvas quiz out on Chapter 4 stuff. Because when I posted it, once again, I did not get a notification. Now, I've only just started. I still have a ways to go in Chapter 4 material, so it's not something that's really pressing. But it's one like it's out there. All right. Do we have mathematical homework 4 questions?
I have a question on 3.4.1, the very last.
Okay.
Showed that the magnitude of A inverse E is less than 1 for some natural metric norm.
Oh, right. Yeah.
Use the proper singular and non-singular, and I went and read through that section B9, and I still just couldn't quite. I was one I really struggled with.
Oh, okay. Well, yeah. So I need to give you a little tidbit about singular and non-singular matrices. That will make this problem doable. All right. So that's for problem 3.
Yes.
Okay. So matrix A, n by n, is non-singular if and only if this is true. Now, from an if-then point of view, this is a rather messy statement, but so if you have a vector x that is non-zero, then a times x must also be non-zero. Okay. All right. So, so in other words, if you have a non-zero vector x and you multiply it by a and get 0, then the matrix is singular. So what you can do is so if you're going to so doing this matrix A plus E, so what you can do for this problem is you're supposed to show that A plus E is non-singular. So try contradiction. Assume A plus E is singular. That would mean that there exists an x, non-zero vector x, such that A plus E times x is 0. So see if you can work with that to arrive at a contradiction. more?
In the algorithm for the QR factorization,
Yeah.
there is no place to store G.
Wait, Cholesky factorization?
QR factorization.
QR factorization.
Given rotations,
Okay. Okay, well, first, any questions more about the homework? Because that's the QR factorization is not in the homework.
The second one.
What?
Yeah. I'm talking about the other homework.
Oh,
The second one.
this is the second homework.
Yeah.
Okay, hold on. Any more questions about the first homework? Okay. All right. So, which problem specifically are you? Can you give me a number?
The algorithm 4.2.2.
Okay.
And the third one.
Exploration 4.2.3.
Yeah. Okay, to implement algorithm 4.2.2. Okay. And your question is again?
And after the follow, the first statement.
Yeah.
After that, there's no place to store the G.
Oh, okay. Well, well, thing is, you're not storing. You don't need to store G from one iteration to the next. So, because it's only Q and R themselves. So, I guess I'm not quite sure what you're getting at, but that because once you have a C and S from givens, then you're just going to use that to rotate 2 rows of R, rotate 2 columns of Q, and then that's it. You're not going to do anything with that C cosine sine pair after that.
I was thinking for every loop, for every I was thinking you have to store the C and X before proceeding to.
Okay. That's something I was talking about, like to have an implicit representation of Q. That has nothing to do with this problem, though. There's no requirement in this problem to store the C's and S's from one iteration to the next, because this algorithm builds Q explicitly. So because really you should do one or the other. You either build Q explicitly as a matrix, or you don't do that. Instead, you represent Q implicitly by storing all the cosine sine pairs and the rows and columns they work on. But we're not doing that here. Yeah. Okay. All right. Any other homework questions of any kind? Yeah, it's really fun because nobody gets that far ahead like that. and nor do we wait till the date's due. Okay. All right. Okay. Well, now I have too much time on my hands. I'm kidding. Hmm. All right. So, well, be sure to keep homework questions coming, like for Wednesday if you're still working on it. Then. Now, as a reminder, we do not meet next week because I'll be away at a conference. And then what happens is, actually, 3 class periods are missed. You have 2 from next week, and then the following Monday, because that's Mardi Gras break. So
one day, and then we have spring break. What?
yeah, yeah. So we have we will have class March 6th. But Wednesday right after Mardi Gras break, and then we have spring break. So we're not seeing much of each other.
Then we see each other Easter. And then
Yeah. And so, just so you know, one thing, what I'm going to do is during Mardi Gras break. So, while you guys are all enjoying yourselves, I'm going to be here, and I will record. I will come to this room and record myself covering something, whatever topic is coming up next. So that's something I'll post. So that's something that you should watch at some point. Let's see, because that'll still be on the chapter 4 material, and I think I updated the schedule somewhat. Let's see what I put here. Whoops, wrong site. Well, it still shows classes on 25th and 27th, but so after I cover this section 4.2, the sections 4.4 and 4.5, I'm going to cover those by my lonesome. Yeah, and so that'll be one big long video for those sections. I'll try not to make it too long, but it's 2 sections, so you can break it up when you watch it. And when we're all back here on March 6th, what I cover then will be independent of that. So I'm not expecting to watch a video during Mardi Gras break. So, but you will want to watch it before you do the relevant homework problems. Okay. All right.
What, are y'all coming to Madison?
No, I mean, only so again, we see the sites come and watch the video.
Yeah, I mean, like, we can sit in here and watch your
God.
Okay. The party, you don't remember that? I'm not driving.
Okay. Yeah.
I saw the high school.
Okay. Well, this is not counts. All right. All right. All right. So in that case, I can continue with 4.2 and computing the QR factorization. Okay. And we'll refer to not the book, but the notes. Just so I'm pointing to the right place there, too. All right. Okay. 2 notes. 6.2. Okay. Now, quick recap. What we want is this factorization. A is equal to QR. A is m by n. M greater than n is the case we care about. So rank of A is n, so n linearly independent columns. And Q is orthogonal, R is upper triangular. So what I covered, so for purpose of solving the least squares problem from last week, but we're still, right now we're just focusing on, we know we need this factorization. In fact, it's been important from several other problems too. How do we get it? And there are three approaches I'm covering. I covered one of them last time. That is Gibbons rotations. So what we're doing is so each row rotation rotates two rows of A to zero a single subdiagonal entry. Okay. All right, because transformation that we're making has the effect of rotating like a vector in two-dimensional space through some angle theta. So the idea is you find the right angle to rotate it to the x-axis so that the y-coordinate is 0, thus zeroing an element. Okay. Now, I realized after class that there was one thing I somewhat goofed on. So this is your matrix A. That's m by n. I've forgotten, in a couple of years since I've taught this class, how tiring it is to write all these x's, which I've been doing all semester long. And we want to zero out all of the subdiagonal entries, these entries. Now, what I said last time, what is the cost of this approach to zeroing out all these entries in terms of m and n? So number of arithmetic operations that are required. So what I said last time was order m squared n. But a sharper indication is actually order mn squared. Now, neither one, and this is actually what I have stated in the book. This is not incorrect per se, and the reason why is when you're using big O notation, describe the complexity of an algorithm or size of something like this. It's meant to be an upper bound of some kind. So all this is saying is that the total number of operations is less than or equal to some constant times m squared n, or mn squared. That's true in both cases. But I call this a sharper bound because this is closer to the real value. Because what I had done last time when talking my way through this is that I estimated the total number of rotations to be on the order of m squared, because you have m minus 1 of them, then m minus 2, m minus 3, and so forth. And you use a formula for sum of the first n integers, which is a quadratic expression, and you get order m squared. But it's actually easier to see, but I'll just use the excuse that I was sick last week, where this comes about, because the cost of a single Givens rotation order n, because you are taking two rows that have length n. You're taking two linear combinations of them. So at most, and some of those will be 0, but the point is at most n entries you're working on each time you do a single rotation. The number of rotations well, it's has to be less than m times n because there are m times n entries in the whole matrix. And you're only zeroing out the ones below the diagonal, so certainly mn is certainly a valid upper bound. So you multiply these two together and you get mn squared. And the reason why, the thing is, this is going to be less than this because, as we must keep in mind, m is greater than n in this situation. All right. We can say exactly how many rotations are required in this case because it's mn minus, and then you're going to subtract off 1, 2, 3, 4, 5, all the way up to n. And we know what that is. It's n times n plus 1 over 2. So that is the exact number of rotations that are needed. Okay. So yeah, I realized after class, I was like, oh, I goofed in saying this a bit. So there you go. Okay. Now, I also want to, before I move on from Givens, to talk about the second approach to QR factorization. We'll talk about practical implementation. Okay. So let's suppose you are given, pardon the pun, this Givens rotation, C minus S, S, C. So in other words, you've computed the values of C and S using the approach I described last time. And, well, and just to have everything a little more self-contained. All right. In the case of A greater than or equal to B, or B greater than or equal to A, to rotate the vector AB to R zeros. In other words, the second element, B, is the one that you want to zero out. So whichever one is the larger goes in the denominator in this value T that you get. And then and this is the practical way. I flubbed this up last times and needed to correct it in the book. So I just want everything clean on the record. Okay. Where sine of A, sine of B, sine is 1 if it's positive, minus 1 if it's negative. So sine of x is just x over the absolute value of x, is how it's defined. Not not defined when x is 0, but that's not going to happen in this case because we're always dealing with the larger of the two. Okay, so so once you have the C and S, to zero a certain entry, A, I, J, where J is going to loop over all columns, and I is going to loop over all rows from below the diagonal down to the bottom. But we're just assuming here we've picked out a particular I and J in our loops, that, two nested loops are running, and how are we zeroing at? Then use A up here is the entry above it, I minus 1J. B is the entry you're trying to get rid of, AIJ. Now, so the actual rotation that happens is I'm going to take, so row I minus 1, so rows I minus 1 and I are the two rows that are going to be affected by this. So it's row I minus 1, and then which columns? Well, you're starting at column J and going all the way to the right. So it'll be columns J through N. Okay. Sorry, I scrolled way too far. Okay. So what happens here is, okay, I have to be careful about this and not, oh, you know what? I can't do these in one shot. Or sorry, I can't do them separately. I have to do it all in one shot. Rows I minus 1 and I together. Columns J through N. The reason why we don't touch all columns is because any columns to the left of column J, we've already worked on them. Those entries down here are already 0. So there's no point. So what you can do is, once you have your C and S, you can form your matrix C, S minus SC. Notice I put the minus down here. It was up here before, now it's down here. That's intentional, it's not a mistake. Because for row rotation, you take the transpose. So this is G transpose times those same rows and columns. All right. So that way, it's going to, so each one of these rows, these two rows, is going to be a linear combination of those same two rows. And it'll have the effect of performing a rotation in each column, because if you're looking at these two rows, each column, that's a 2 vector. So it's rotating each one of those 2 vectors, and it's only going to zero out the second entry of one of them, the one in column J, because that's the entry you're trying to get rid of. It's still going to affect the rest of the rows, just because that's what you're doing. You're taking A and multiplying on the left by a given row rotation. It's going to affect the entire row. Now, to the left of column J, it's all 0 anyway. But this is what it takes to zero out AIJ. So what MATLAB is doing, and this is the actual MATLAB statement, well, you had to write this out in MATLAB syntax, but is it's going to extract this submatrix from A, so those two rows and those columns, carry out the multiplication, and then write the result back into A. Now, in the algorithm that I gave last time, it also had to rotate two columns of Q, which is similar, except instead of multiplying on the left by G transpose, you're multiplying on the right by G. But a key difference there is that for doing those column rotations, unlike here, where you only had to take part of a row, you have to use the whole column. And the reason why is A is being reduced to upper triangular form, column by column. So you know there are certain entries that are becoming 0. That's not the case of Q. So these are things to keep in mind to make sure your algorithm is not performing wasteful operations. So one of the homework problems for the second assignment is implementing QR factorization, like using Gibbons rotations or the other approaches that I'll be talking about. So these are things to keep in mind to make sure that it's done reasonably efficiently. Because if you just do it the most straightforward way, there's a lot of waste going on. Okay. So any questions about, or you're all brain dead by now? Okay. Well, that's why I record these. Okay. All right. Now, but this is only one of 3 approaches for QR factorization. And so this one, I mentioned last time, has its advantages. It's quite flexible. Like if you have certain entries of A that are already 0, you don't want to waste. So you can maybe just do a few select rotations, or if you need to update if your matrix A is updated in some way, like inserting and deleting rows and columns, and you want to update the QR factorization, Gibbons rotations are helpful for that. But if you have a general case matrix to reduce to upper triangular form, and you're trying to minimize floating point operations in doing that, Gibbons is not the best. So there is a faster way. It's not much faster, but it's something. Although personally, my preference for the approach I'm going to do is that Gibbons rotations, they're just not destructive enough. And the Gibbons rotation is only going to zero out one entry at a time. So you're going to have to use a whole bunch of them to target the order m times n entries and wipe them out. So each one is a little bitty foot soldier that's just going after one entry. I want something that's just going to wipe out a whole bunch of entries at once. That's just going to trash a column in one shot. And that's what this next approach is going to do. All right, the glare zone. It seems to get worse. Yeah. What I'd really like to do is zero out that one fluorescent light that's causing this.
I mean, you can turn off the lights, so we might sleep. I mean, you gotta
Yeah, maybe once
choose your
solve
poison.
problem, create another.
Yeah.
Okay.
Yeah, no, we definitely zoned it down. That's pretty good. Keep going. Give or take.
Okay.
You're a little on the inside of the glare, so just.
Yeah. Well, I'm not sure if it's practical to use that part of a board anyway.
It's not. You can erase my semicircle.
You didn't erase the board after class.
That's the only thing I put on the board. I'm sorry.
No, there was other stuff down there.
That
I
wasn't
erased it.
mine.
Oh.
That was there when I came in.
Oh, so Candace left that.
Yeah. Thanks for cleaning up our messes.
Okay. So, second approach, QR, is household reflections.
In the glare zone.
So, as far as I know, these actually were invented by Householder. Alston Householder is his name. Unlike Gibbons rotations that were invented by Jacobi and used by Gibbons. So, mathematical appropriation. So what is a Householder reflection? So, also known as just a Householder transformation. I like to use the word reflection because it's more descriptive of the action that it takes. Okay, so I should check my notation here. Okay. And don't ask me why I referred to a Householder matrix using the letter P when H would have been more intuitive, but too late, the book's published. Okay. So P is the identity matrix minus, okay. All right. So 2 VV transpose, where V is a vector of magnitude 1. In the 2 norm sense. Now, so this matrix has some unusual properties. So first, I'm going to take its transpose. And for that, we need the properties for transpose. Well, now a transpose of a sum is just a sum of the transposes. Okay. Now, identity is a symmetric matrix. So that's just identity itself. And then remember, transpose of a product is a product of a transposes in reverse order. So I have V transpose transpose, which is just V again, and then V transpose. So it's the same. So P transpose is equal to P. So we say that P is symmetric. Note the expression here, VV transpose, that is an outer product. I've mentioned that before. So something we're going to see quite a bit of in various settings. Okay. But a second interesting property that P has if I were to compute P transpose P, well, P transpose is P, so that's the same as P squared. So identity minus 2VV transpose squared. So I'm going to write all that out so we can FOIL it. So when we go ahead and FOIL it, we have identity, and then all this times identity, so it's that itself. And then this minus 2VV transpose times identity again. So those terms could be combined. And then I have V's multiplied together. Now I'll have plus 4, but I have to remember respecting the non-commutativity of matrix multiplication. So I'm going to have V transpose, of any other V transpose. Okay. So now I'm trying to simplify this. So these two terms can be combined, so minus 4 dV transpose. And then here, V transpose V. When we have an expression like that, what kind of operation is that? V transpose V. What do we call that? It's a dot product. So dot product of V with itself. So V transpose V is a number. So we can move that wherever we want. So then I still have a V and a V transpose. Now, V transpose V, the dot product or inner product of a vector with itself, that is the magnitude in the two-norm sense squared, which in this case is 1, because that's what I assumed at the beginning. So that goes away. So now I have identity minus 4 VV transpose plus 4 VV transpose. Yeah. So everything goes away. And left with identity. That's consequence of using a 2 in there. Okay, now, so what do we call this? What kind of property did I just show that P has? Well, I showed that earlier, but what does... So, orthogonal. P transpose P is identity. When you have that for a square matrix, the matrix is orthogonal. So, okay. So, this is actually rather unusual. To have a matrix, having a matrix that's symmetric is not unusual, or orthogonal is not unusual, but to have both is unusual. And a consequence of that, okay, the orthogonal and symmetric. Because symmetric means P transpose equals P. Orthogonal means P transpose is equal to P inverse. What can we say if we put these two together? What?
P is equal to it first.
Yes. P is its own inverse. Now, because normally, if I just asked you, give me a matrix that's its own inverse. Of course, the most obvious choice is answer is identity. And then I think, well, okay, well, tell me another one. Well, you might think of minus identity. Just like in real numbers, the only ones that are their own multiplicative inverses are plus and minus 1. But it turns out that when you're dealing with square matrices, you're not limited to that. So now we have this whole class of matrices where each one is its own inverse. Now, so how is that going to help us with QR factorization? We want to take a matrix A and reduce it to upper triangular form. Okay. It's because we can use it, so a transformation like this can be used to zero out entries. So, given some vector, a non-zero vector x, what we want to do is find some householder matrix P, so something of this form, such that if I multiply p by x, then what I get is some constant alpha times E1. Now, E1, recall, is the first column of identity. So it's going to be a vector that has all zeros except for a 1 in the first position. So this vector is going to have an alpha in the first position and all zeros after that. So in other words, I want to find a household matrix P that will wipe out, when applied to X, will wipe out all of it except for the first element. So this is how a householder reflection can help me with QR factorization. If I take X to be the first column of A, then I can apply this household reflection, wipe out everything below the diagonal of that first column. Then I can move to the second column and wipe out everything below diagonal again, so wiping out one element less. Then I can keep going. So if I can find, for any given X, this household reflection that will do that, that will lead to an algorithm for QR factorization. Okay. Now, first, alpha can't be just anything. Because when you multiply a vector by an orthogonal matrix, and P is orthogonal, what property of that vector is preserved? When multiplied by an orthogonal matrix. What? Length. So the length of this vector, alpha E1, has to equal the length of X. So alpha must be plus or minus the Euclidean length of X. So we're limited to that. But that's okay. Now, V determines what P is. So we got to find the V that will do the trick, that will make this happen. Okay. So we had to solve this equation. P times X, which is equal to identity minus 2V transpose X, is equal to alpha E1 for V. So we just have to find the V that's going to let that be satisfied, assuming that it's possible, which you're going to see that it is. Now, to do that, let's distribute. So now I have identity times X. So X minus 2V, and then I have V transpose X, which remember is a dot product, therefore a number. That is alpha E1. Okay, now V is only occurring in this term, so I'm just going to rearrange. Isolate anything involving V on the right side. So X minus alpha E1 is equal to V transpose X, which is a number, times V. Oh. Now, at first glance, it seems like a very difficult equation to solve for V, because V occurs in two places on the right side. It's in this inner product with X, and it's also multiplying the whole thing. But here's where we use what we know about V. What do we know about V before this process even starts? What's our assumption about V? Yeah, the magnitude is equal to 1. In other words, so because the thing is, this right side is a scalar multiple of v. It is parallel to v because you have v times some constant, this 2v transpose x. Okay. So what that tells us is the left side also is a multiple of v. So v has to be equal to the scalar multiple of this vector, x minus alpha e1. And because it's a unit vector, we had said v equal to x minus alpha e1 over the magnitude of that. So there you have it. This is our v. Now, one potential sticky point here is, I know that v has to be a unit vector, which is why I'm doing this. But notice here I said alpha, I said also, alpha has to be the magnitude of x, but I had to allow plus or minus. Here I didn't put plus or minus. And it's like, well, it seems like an oversight. But it turns out it's not, only because of how v is actually used. Here, or in v transpose. If I was somehow had the wrong v, I was off by a sign, it would cancel out in here. So it really doesn't matter whether I said v equal to plus or minus this. The effect of a householder reflection on x is going to be the same. So this will work. Now, what I'd like to do is simplify this a bit if I can. Because I have this expression down here. So I have to compute the magnitude of this vector. If I could simplify that at all, that would be a good thing. So if I look at x minus alpha e1, and I'm going to compute its 2 norm squared, just because I'll just take a square root after. So that is the dot product of x minus alpha e1 with itself. So that's going to be x transpose x minus, because the dot product is commutative for real vectors, 2 alpha e1 transpose x plus alpha squared e1 transpose e1. But this can be simplified. Okay. This is the 2 norm of x squared. So, in other words, alpha squared. And then e1 transpose x, that's a dot product of this vector e1, well, without the alpha. Well, actually, literally is this vector. The dot product of this vector with x. What do? You multiply corresponding components and add them up. But most of these are 0. The only non-zero component is the first one. So I'm going to get 2 alpha x1, the first component of x. And then here, the dot product of e1 with itself, it's a unit vector, so it's going to be 1. So it's going to be plus alpha squared. And, well, alpha is already known to be plus or minus the magnitude of x. So it's going to be 2 alpha squared minus 2 alpha x1. So that is my denominator. So once I know what alpha is, plus or minus, I can subtract that off the first component of x and then scale. So it all works out quite nicely. In the notes or the book, I do some manipulations that don't really make a huge difference in terms of the algorithmic complexity, but so I'm not going to spend time on that. But so once you have this denominator, you just divide the entire vector by that, and then you have your v. Yes.
You do put it in the square root,
What?
right? In the square root.
Well, I do need to take a square root of this. Yes. Is that what you're asking? Yes. Okay. Yeah. So that's going to be. Okay. Now, is there any questions up to this point?
Whenever you pull that out to begin with,
Yeah.
your outer and inners, could you discuss that again? How did you combine those?
These terms?
To go
Oh,
right,
yeah.
right above it.
Because so I have minus alpha E1 transpose X, and then minus
that.
alpha X transpose E1. Dot product is commutative.
Okay.
Yes, that's for real vectors. That's yeah.
All right.
Okay. You have a question? Okay. So actually, if I were to summarize the computation of V. Okay. From a given X. And this is where also I should resolve the plus or minus thing for alpha. Okay. So let's alpha be equal to minus the sine of x1 times the 2 norm of x. Now, I need to explain why I'm suggesting this choice. And I'll do it as soon as I write down. So V1, the first component of V1 is going to be x1 minus alpha over the denominator that I worked out over there. Okay. Because let's suppose that x1 is positive. Then sine of x1 will be 1, so that means that alpha is going to be negative. So negative and a negative will make it a positive. So in other words, if alpha is chosen, the sign of alpha is chosen, so that this is actually an addition, not subtraction. In other words, both numbers being added have the same sign. Okay. All right. So, why is that a good idea? Yes.
Where is this 2 coming from? The 2 alpha squared.
Because this, remember, alpha is plus or minus the 2 norm of x. So that's alpha squared, combining with this alpha squared. So why is it that I want an addition, not a subtraction up there? This is a 460 thing. We only took it 4 years ago. Some people took it more recently, though. Why do we not like subtraction? Yeah, Catastrophic cancellation.
Yeah.
Um,
Say that again?
catastrophic cancellation.
Catastrophic.
Because if x1 and alpha were nearly equal and we subtracted them, then that'd be bad. Yeah, the error would be much larger than usual. So we make sure that we're actually performing an addition, gets around that. So it's not likely to happen, but you just never know. So again, with the assumption that x1 being positive leads to alpha being negative. So what that means is that would be negative, and this would also be negative, thus making the overall thing positive underneath. So we don't have to worry. There's no way we're going to take a square root of a negative number. All right. So that's the first component of V. And then the second component, well, we have x minus alpha E1, but that only affects the first component. So the second component is going to be x2 over the same denominator. And then similar for third component and so forth. So we're just going to compute this denominator once and keep dividing by it all the way down to Vn. Okay, so really, yeah, all we're doing is we're figuring out what alpha is based on the sign of x1, subtract it off only from a first component of x, and then we scale by 1 over v's square roots, and that's it. That's our v. That's our magical v. That so that when we multiply the resulting householder reflection with x, it wipes out everything except the first component, which is now going to be equal to plus or minus the magnitude. Okay. So questions about what happened here? Now, before returning to QR factorization, one other point I want to address is, why do we call it a householder reflection? Where does the term come from? And we can see that by how P acts on certain vectors. So I compute P V. So I multiply, so I use V to make P in the first place, and then multiply it by V itself. So that's going to be identity minus 2V V transpose V. So that's going to be V minus 2V V transpose V. And we see we're multiplying an outer product by a vector gives us an inner product. But this is 1. So we get V minus 2V, which is minus V. So if you use a vector V to make a householder reflection and you apply it to the vector V itself, it negates it. But now, suppose I have a vector x that is orthogonal to V. Then Px is going to be x minus 2v v transpose x. But that's 0. So we just get x. So if we consider how P acts on any vector in the whole space, you could break it down into, if you're in an n-dimensional space, you could break it down to n orthogonal directions. The direction of V, and then n minus 1 directions that are orthogonal to V. P will preserve the components in all of those dimensions, except for the one parallel to V itself, which is going to negate. So if I were to describe in words what P is doing, geometrically. That is, P X is the reflection of X across the hyperplane that is normal to V. So what happens is, if you have some plane and so V is the normal, and this is your vector X, then this vector would be Px. So the component of X in a direction of V that's this component right here, is negated. But all other components of X stay the same. So that's what we call reflection. It's reflecting whatever vector you multiply it with across a given hyperplane. Okay. So questions about that? Okay. Now, time here. Okay, almost 6. Dang. Okay. Well, that's okay. I'm not going to knock us behind again. All right. So I want to explain how we. Oh man. Typo in the book. Dang it. It's just a misplaced. It's a missing parenthesis, but still. Okay. Love finding all these things months after the book's been published. Okay. And first, second zillionth edition. Or zillionth edition. Okay, so how we actually use this for a QR factorization. Okay. So this would be householder QR as opposed to Gibbons QR. So I need to make sure my notation is consistent. All right. So the idea is, starting with A, you're going to multiply on the left by several householder matrices, n of them, one for each column, to reduce A to upper triangular form R. And that would mean that Q would be the product of all of these in reverse order. Okay. normally when I did this with givens, it's the exact same idea. I had to transpose everything, but I don't have to transpose these because household reflections are symmetric. Now, so I need to describe what each of these H's are. So each householder matrix Hj is an identity matrix of size j minus 1 at the upper left. 0, 0, and then a smaller householder matrix, which I'll call Hj tilde, in the lower right block. Now, Hj tilde, and this is going to be of size, let's see, m minus j minus 1 times m minus j plus 1. So for instance, for j equals 1, it's the whole matrix. It's the same size as A, m by m. And it keeps getting smaller from there. So this is a householder matrix in usual form, identity minus 2. And I'll call this Vj transpose. So the way we get V is, if we know what X is, the X that we want to wipe out entries out of, we want to 0 entries in, that determines V as I wrote down over there. So each Vj comes from A, rows j through m, so row j all the way to the bottom, column j. So for instance, when j equals 1, we take the entire first column. And then when we move to the second column, we take everything except the first entry, and then except the first 2, and so forth. So we keep using smaller and smaller portions of columns of A. So in other words, this is what we're referring to as X for over there in our V getting procedure. The other thing I want to point out is this is not referring to the original column of A, except the first time around, because once we apply the first householder matrix H1, that's going to affect all of A. So as we move to the second column, whatever the second column is at that point, that's what we take to be our X. I found it out the hard way. I was trying something like, what if I compute all these householder matrices up front and then apply them? Well, that's wrong. You have to take into account what's affected by them. Not sure what I was thinking there. Okay, so we keep applying householder reflections to a smaller and smaller portion of A until the entire thing is upper triangular. Another way to look at it, though, is instead of looking at it like this, I could say that, let's see, oh, you know what? I'm going to call these tilde also, just for consistency here. Because what I could say, equivalently, is this is identity minus 2 Vj transpose, where Vj, no tilde, has zeros up top, Vj tilde underneath, where here we have j minus 1, 0 entries up here, and this is everything else down here. So, so both Hj and Hj tilde are, strictly speaking, householder reflections, just with the appropriately sized V. And the fact that this upper part here is 0, that just means each household reflection is affecting less and less of a matrix. Okay. So that's the idea behind the algorithm. Okay. Now, one thing I want to point out is since vector v, whatever v you're using, is enough to determine the entire household reflection, you never ever actually explicitly form this full matrix, Hj or Hj tilde. Never explicitly form a household reflection. Because what are you doing with household reflection? You're multiplying it by a vector, either on the left or the right. So if you just work out what that multiplication is, and then so to give you explanation as to how wasteful it is to go the other way. So let's look at the two matrices P and A, be m by m, just for simplicity. So if you just go ahead and compute PA, this way, identity minus 2 V transpose A. And you form this explicitly. So you go to the trouble of computing identity minus 2 VV transpose, you compute all those entries, and then you multiply that by A. The cost of that is order m cubed floating point operations, because that's a matrix multiplication, which in general is order m cubed. Okay. But if you don't do that, you don't explicitly form P, and instead you actually distribute this. So it's A minus 2 V transpose A. Now here you still have to be careful, because suppose I form this, I'll indicate parentheses here, I'll still form this explicitly, VV transpose, outer product. Also, order m cubed. So you've accomplished nothing in terms of savings. But now here's where we use the fact that matrix multiplication, while not commutative, is associative. So I'll parenthesize differently. If I do that, huge difference, it's order m squared. I've knocked off a whole order of magnitude of work. The reason why is, instead of doing a matrix multiplication, this is a matrix vector multiplication, known in business as a MATVEC. Now, once I have this is going to be a row vector times this column vector. That's an outer product. So I have a MATVEC, then I have an outer product, and then a matrix addition. All three of those operations, MATVECs, outer products, matrix addition, are order m squared operations. So it's imperative when we have a householder reflection that we apply this way. Now, here I've applied P on the left. If you're doing QR factorization and you want to generate Q explicitly, you have to apply it on the right also. But the same idea can be used. Again, you parenthesize appropriately, that operation will also be m squared instead of m cubed. All right. So that's a very important point there. The algorithm for householder QR 4.2.5, that's how it's numbered in the book anyway, but it is featured in the notes. You'll see, except for my missed parenthesis there, that the operations are written out like this. And you can also see which rows and columns are affected. And so what we have is, you can see that a household reflection is applied on the left to reduce A to upper triangular form, and it's applied on the right to carry this out. So you start with identity, and you apply H1, H2, and so forth on the right to explicitly form Q. Yes?
Is that m minus j plus 1 times m minus j plus 1 underneath the h tilde?
Yeah, that's the dimensions.
Okay, I was just making sure.
Yeah.
'Cause,
Okay.
I can't see on that.
Oh, okay. Oh, whoops.
It's okay.
All right.
I'm getting a prescription.
Oh, okay. Whatever you gotta do. All right. Now, as I mentioned last time with Gibbons rotations, you don't need to form Q explicitly. If you save the cosine sine pairs and also indicate which entries they're used for, you can implicitly represent Q that way. Same is true with householder QR. If you store these vectors, the V tildes, only those, then you can at least save some storage. Not a whole lot. Well, actually, yeah, compared to storing Q as an m by m matrix, you only have n of these vectors, and they're all of decreasing length. So actually, if m is much larger than n, then the storage savings is significant. Because, like I said, you never really, or I won't say never, but for ordinary usage, like just solving least squares problems, you don't need it to. You don't need to explicitly store Q, because if you have some way of applying the household reflections, then you can apply them to the B from your least squares problem, just like you apply them to A to reduce it to upper triangular form. I mentioned that with Gibbons rotations. It's the exact same idea. So whatever you did to A, you also did to B, kind of like with Gauss elimination of your augmented matrix, and then you can solve your least squares problem. Now, as far as the cost, of householder QR, it's order mn squared, same as Gibbons, but it's also 2/3 the cost of Gibbons. So the order of the complexity of the two methods is the same. It's just that all I'm saying is the number of operations is roughly a constant times mn squared. So the constant for householder is 2/3 that of a constant for Gibbons. So that's one reason people have for preferring householder QR over Gibbons for like the general case of QR factorization of a general m by n matrix A, is that it does save you some arithmetic. Just like for a symmetric positive definite matrix, don't use Gauss elimination, use Cholesky because you're saving half the operations. So we have similar savings here with QR factorization. But like I said earlier, Gibbons has its advantages, flexibility for matrices that have a certain structure or good for updates. So householder is not so good for that. So that's what happens a lot with these kind of problems. There's different methods for solving them, and there's no out-and-out winner. It just depends on the situation. That's why it's good to be familiar with all of these, including what I'll talk about on Wednesday, which is Gram-Schmidt orthogonalization, which, again, has its advantages and drawbacks. So, all you ever wanted to know about QR factorization, or a whole lot more than you wanted to know, I'm sure. So, okay. Well, it's 6:14, so I figure we've all suffered enough.